Hi, everyone. Welcome back. I hope all of you are staying healthy, keeping safe. So we're almost there, almost done. 3 more lectures to go. In this lecture, what we're going to do is we're going to continue with some reactions from Chapter 8, alkenes, and Chapter 9, alkynes combined. And the reactions that we're going to see today, they again have like a common theme. So in the previous lecture, we looked at hydrohalogenation and halogenation. So there was that theme of halogenation. How do you add a halogen to an alkene or an alkyne? That's the theme that we looked at. Today we are going to look at hydrations, or what happens when you add water to alkenes. Now we've seen this before, so there's going to be some similarities, some overlap in terms of mechanisms and reactions. But again, we're going to see this for alkenes as well as for alkynes. Okay, so first we're going to talk about acid catalyzed hydration of alkenes. So again, we are going to see this for alkenes first, and then we can go ahead and apply the reaction to alkynes. Although in this particular case, there are some deviations. Okay, so alkynes, the mechanisms, there are some similarities, but the product is not what we would expect based on the product that we get in the hydration of alkenes. So this is coming from section 8.5 in the textbook. And what this reaction does is, and if I remember correctly, I don't actually, so I don't know what number we are on right now. I think this is probably the 4th or the 5th reaction that we're looking at, but this is what we're doing, acid catalyzed hydration. And what this reaction does is, again, for you to like basically keep in mind, okay, what this reaction does is it converts alkene into an alcohol. Okay, converts alkenes into alcohols, and this is generally the more, not generally, this is always the more substituted alcohol that's obtained. Okay, so again, throughout this chapter, and I think towards the latter part of like chapter 7, I've been using these terms: more substituted, less substituted, and these I think these are good indicators, something to like basically keep in mind and relate your starting material to the product. Okay, so it will give you the more substituted alcohol when we do this reaction. So as an example, let's say if we have an alkene, that's an alkene molecule. Okay, now just by looking, and we are doing a hydration, which is the reverse of the dehydration that we talked in chapter 7. So when we went over dehydration, I said this is a reversible reaction. So dehydration converts alcohols into alkenes. Hydration converts alkenes into alcohols. Okay, so this is a hydration reaction, and this reaction is usually done using acid again, catalytic amounts of acid. So you only need a tiny bit of acid. Okay, so and we use dilute acid. So when we did the dehydration, we used concentrated acid, which was a very strong acid, very little water in it. Now we're using dilute acid. So there's more water, there is some acid in there. Okay, dilute sulfuric acid. And again, for all of these acid catalyzed reactions, I mentioned this earlier, that a good way to visualize this is what we have in our system is hydronium ion, okay, which is basically water molecule and a proton. So we have a lot of water and we have a proton to resemble the acid in here. Okay, so we take an alkene, we're doing a hydration on it. Hydration would mean addition of water. So essentially what we're adding is water. And the key here is the alkene is converted into an alcohol, but the more substituted alcohol. So if you look at our alkene here, we have the carbons that are double bonded to each other, where the pi bond is, okay? And you can notice that this carbon on the left is the more substituted carbon, because this does not have any substituents on it. It has hydrogens to it, whereas this carbon has a methyl group to it. So it is more substituted of the two. So that means when we do this reaction, what we're going to get is we're going to add water, H and OH. So the hydroxyl ends up at the more substituted carbon, so that we get the more substituted alcohol. Okay, so in here we've added a hydrogen to the less substituted carbon, so the hydrogen is there, and the hydroxyl is added to the more substituted carbon of the pi bond. So that's a way to like basically kind of memorize this in a way, you know, or to remember this easily. Okay, so alkene becomes the more substituted alcohol. So we'll look at a few more examples of this, but let's work through a mechanism first. Okay, what happens in this reaction? How does this reaction work? And the mechanism for a hydration reaction is the reverse of a dehydration reaction. So we have alkene, okay, and what we have here is acid. So I'm going to use the hydronium ion to represent the acid, okay? We have HOH2 plus lone pair on that oxygen. So we have a hydronium ion. Between these two, remember for alkenes, the alkene always behaves as a nucleophile, okay, in most of its reactions. In fact, it is behaving as a nucleophile. So the pi bond on the alkene is going to go and attack that proton, because that's our electrophile. So the pi bond goes and attacks that proton. Electrons go to the oxygen. So in a sense, the alkene is getting protonated over here. Now, when the pi bond accepts that proton, okay, the pi bond accepts the proton. Now the proton could end up as a hydrogen at the more substituted or the less substituted carbon. So that's something that we've already seen, that in this reactions or in these reactions, the hydrogen actually goes to the less substituted carbon, because that would then give us the more substituted carbocation. So there's the hydrogen and there's the carbocation. Now realize that it's a hydrogen, so in a bond line structure we don't really have to show it. Okay, there were two hydrogens here. Now the hydrogen is added, so we get a methyl group. So we could just leave it at like that. Okay, I drew it out just to show you, but now we don't have to, because it's a bond line structure. So we have a methyl, and we have a carbocation here. So we get that carbocation, and again, these reactions are reversible, so this can go forward or backward. So we get the carbocation. After we have the carbocation, what happens is in the next step, so we've got the carbocation, and that would give us the water molecule. I will draw the water molecule along with it here. Okay, so we have the water molecule now. And so what happens is in the subsequent step, water molecule goes and attacks that carbocation. Again, remember that carbocations are sp2 hybridized, so they are trigonal planar. That means the water molecule can attack from both faces of the carbocation. Okay, so carbocation attacks that, water molecule attacks the carbocation. That would give us an oxonium ion. We saw this in the dehydration reaction as well. This step is also reversible, because the oxonium ion could leave, and that would give us the carbocation and the water molecule back. So we get that. And then from here, again, another reversible step, an additional water molecule. There's a lot of water because this is dilute acid. Okay, so another water molecule comes in and deprotonates. Okay, it abstracts a proton from this oxonium ion, which puts the lone pair back on that oxygen atom. And so we get the alcohol. and plus we are going to get a hydronium ion because the water picked up that proton. So water is acting as a base, weak base, and it's accepting that proton. So what you notice is we started with a hydronium ion, we end with a hydronium ion. What that means is you only need a tiny bit of acid for doing this reaction. So that's why we call it acid catalyzed. So both hydration and dehydration are acid catalyzed reactions because you start with an acid, you end with an acid. So the acid basically comes out. Okay, so it's just a catalyst. So it participates in the reaction, but it is not used up during the reaction. So we get that hydronium ion back. So this is the mechanism of a hydration reaction, how we get an alcohol from an alkene. And the reason we get the more substituted alcohol is the more substituted because the more substituted carbocation is formed. And since we have the more substituted carbocation, the nucleophile, which is the water here, attacks that carbocation, so we get the more substituted alcohol. Okay, so that's the mechanism of a hydration reaction. Let's look at a few examples. So now we can go ahead and apply this to a few scenarios here. So let's say we have cyclohexene and we react this with dilute sulfuric acid. And dilute sulfuric acid basically, again, realize is hydronium ions because this is water, a lot of water and some acid. So that's equivalent to like the hydronium ion. Even if it's a concentrated sulfuric acid, you could treat that as hydronium ions in general. Okay, there's some water in the in concentrated sulfuric acid also. So we have this. Now when you look at the alkene here, notice how these carbons, they're equally substituted. This has one substituent, that also has one substituent. So that means in this particular case, there is there's no competition in terms of where the hydroxyl would land. So we are going to get an alcohol where the hydroxyl is on that carbon, or it could be on this carbon. And in this case, it's basically identical because there is symmetry in the molecule. So we get that alcohol as our product. You know, that would be our product. And we don't have to show the plus H3O plus because it's right here. You know, it is basically used up and it comes back out. So that would be our product. If we used a different molecule, let's say we have a cyclohexene, which has a substituent now, and we do the same reaction. So dilute sulfuric acid. Okay, so we are doing a hydration. So the dilute should always trigger this thought about, or it should help you connect with hydration compared to concentrated, which should always be connected with dehydration. Okay, dilute sulfuric acid, carbon, carbon. This carbon has one substituent. That carbon has two substituents. So that's more substituted. So that means in this particular case, our product is going to be that alcohol. So the more substituted alcohol, okay, whenever we have that choice. So those were like two examples. Now let's look at a few examples where stereochemistry would be important, okay? So think about an alcohol or an alkene like this. Let's say we have this alkene and we do a hydration reaction on this alkene. Less substituted carbon, more substituted carbon. So that means our product is going to be this alcohol here. And now we've generated a chiral center. This molecule is chiral. And since there is a chiral center and there was a carbocation intermediate, what that means is this molecule is going to be a racemic mixture. So we're going to get plus and minus. Or you could put the hydrogen on a wedge and write plus enantiomer, okay? So we're going to get a racemic mixture. In fact, if you just show the star, I think in some sense that says that you've identified that there is a chiral center in the molecule. Okay, so that means you're saying there could be possibilities for both enantiomers to be formed. So plus and minus, you get both enantiomers here. Okay, this will apply to open chain molecules as well. So let's say we had a molecule like this, less substituted carbon, more substituted carbon in the alkene, and we do the reaction with dilute sulfuric acid. Hydroxyl is going to go to the more substituted carbon. So that's where the hydroxyl would end up. And we've got a chiral center again. Okay, so this should also be a mixture of enantiomers, so plus and minus would form together. Okay, so those are some examples. Now, I want to show you something else, and hopefully you'll be able to identify this, which is actually right here. So let me show you this example here. Use this example at the top. Now, when we do this reaction, I'm going to redraw this reaction here. Okay, when we do this reaction, we're going to make two alcohol products. We're going to make this alcohol plus we are going to make that alcohol, and most likely this is going to be our major product. So how do we get that alcohol? It's the question. So again, I want you guys to think about it a little bit. The alcohol, the hydroxyl group should have been on this carbon, the more substituted carbon between the double bonded, among the double bonded carbons, but somehow it's moved. So when do we see that move happen, or when do we see that shift happen? It's when we have rearrangements. And it should not come as a surprise because we have a carbocation intermediate in this reaction. Okay, so let's go over this mechanism one more time. And we will include the rearrangement in here. So if we start with this alkene, reversible reaction, reacts with a hydronium ion, the pi bond goes and attacks, electrons go to that oxygen in the bond, go to the oxygen, so that would give us a carbocation, plus it's going to give us water molecule. Now when this water molecule, okay, and I'm going to make it specific mechanism for major product, okay, when the water molecule goes and attacks the carbocation that's generated right now, it will lead us to this product. But we have this carbocation and there's a carbon next to it which is tertiary in nature. This carbon is secondary, this is secondary, and this carbon here is tertiary in nature. And so the hydride can migrate. We get a hydride migration. And now this is going to be favored in the forward direction. Okay. And because of that, now we get the carbocation at the tertiary carbon now. Okay, this one here is chiral. Okay, we get the carbocation and the tertiary carbon, and now water molecule can come and attack that carbon. With one lone pair, one positive charge on that water molecule. And then finally, an acid-base reaction where more water comes in, deprotonates, and it will give the hydroxyl plus a hydronium ion. So that will be the mechanism of how we get to that rearranged product. And that product does not have a chiral center. Okay, that carbon is not a chiral center. So that will be the mechanism. And again, realize that this is a reversible reaction. So that means you have to you push the reaction to completion by changing stoichiometry of reactants. That's one way to do it. So that's why when we are doing this reaction, we're using dilute sulfuric acid. So that's like a lot of water. And so essentially we're pushing the reaction forward, to the products, so that the equilibrium favors the products, because we are loading up on our reactants, or at least one of our reactants. If it's not the alkene, but it's like water, that's one of the reactants that's needed. We're loading up on that, and that pushes the reaction forward. Okay, so that's the acid catalyzed hydration of alkenes, which converts an alkene into an alcohol, and specifically the more substituted alcohol. Okay, we will do some more videos, so I'm going to break them up into like small modules, like one video for like each reaction. So we're going to look at another reaction which is very similar. Okay,